The Big Bang Theory, a cosmological model that explains the birth of the universe, has been a cornerstone of our understanding of the cosmos for decades. However, as technology evolves, so does our understanding of this monumental event. The latest tool to aid in this exploration is the time machine, the James Webb Space Telescope, or JWST, which is revolutionizing our understanding of the Big Bang Theory and our origins of the universe. Webb's ability to view the universe at infrared wavelengths has opened up new avenues of research in cosmology. Scientists are now able to look further back in time to see the first galaxies that formed in the early universe, with a level of detail that was previously unimaginable. This has enabled researchers to delve deeper into the mysteries of the universe, uncovering new insights about the Big Bang and the early universe. In other words, it's time to revisit the Big Bang Theory. Join us today as we dig deep into how the James Webb Space Telescope just upended our understanding of the cosmos. Perhaps the greatest achievement of the late 20th and early 21st century astrophysics is the arrival of a consensus model of the entire universe, the lambda-centium cosmology. For countless generations of humans, we've marveled at questions such as, what is the universe? What makes it up? How far, to the limits of what it's possible to observe, does it go on for? How did it come into existence, and how long ago? How did it grow up to be the way it is today? And what will its ultimate fate be? Today, after unprecedented measurements of galaxies all throughout cosmic history, all sky imaging of the universe at microwave wavelengths, and thousands upon thousands of supernovae and other transient events all across the universe, we finally have our answers to these questions. Our universe is made of 68% dark energy, 27% dark matter, and just 5% normal stuff. And it all began from a small, dense, nearly perfectly uniform state some 13.8 billion years ago in a hot Big Bang, and has been expanding, cooling, and gravitating ever since. At least, that's the consensus picture. Recently, however, a challenge to that picture has gotten some pretty popular attention, based on the latest findings from the James Webb Space Telescope, whose unprecedented infrared eye has been rewriting what we thought we knew about the early universe. Astronomers have long thought that the newly minted galaxies that began merging together just after the Big Bang, about 13.7 billion years ago, were too fragile to boast any noticeable structures like spiral arms, bars, or rings. Those galactic features were thought to form during a time at least 6 billion years after the Big Bang. According to the new study, however, these delicate shapes could have manifested as early as 3.7 billion years after the Big Bang, which is almost at the beginning of the universe. According to Christopher Consolis, an astronomy professor at the University of Manchester in the UK and a co-author of the new study, said, "Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years." The new findings come on the heels of another announcement presented by a different group of researchers, also based on JWST data, which showed that these early galaxies produced far fewer heavy elements than previously expected. However, the relationship between a galaxy's chemical composition and its evolution into a well-defined structure is not very well understood. Much of scientists' previous understanding of the galaxy evolution came from data gathered by the Hubble Space Telescope, or HST, which is legendary in its own right, but still has only so much resolution. While the HST data showed early galaxies had irregular shapes, as was expected during galaxy mergers, higher resolution data from the JWST is peering deeper into the universe to reveal that those early galaxies actually had well-defined structures, like our own Milky Way. The new findings were based on an analysis of 3,956 galaxies, which astronomers say is the biggest sample that has been studied thus far with JWST data. Like Leonardo Ferreira, an astrophysicist at the University of Victoria in British Columbia, Canada, and the lead author of the new study, said in a statement, quote, "For over 30 years, it was thought that these disk galaxies were rare in the early universe due to the common violent encounters that galaxies undergo. The fact that JWST finds so many is another sign of the power of this instrument, and that the structures of galaxies from earlier in the universe, much earlier in fact, than anyone had anticipated," he said. According to the new study, the team classified the sample set of close to 4,000 galaxies from the early universe by shape, like disks, point sources, and spheroids. Team members further classified them as smooth or structured, with galaxies in the latter group featuring bursts of star formation and indications of mergers with other galaxies. Results showed that relatively well-defined structures in the universe form a lot quicker than previously thought, following what is known as the Hubble sequence, which is the standard classification of galaxies by their visual properties as ellipticals, lenticulars, and spirals. The latest findings suggest a need for new ideas that explain how galaxies evolved over the past 10 billion years. And that wasn't something scientists really expected. But the standard model of the universe in cosmology just got even more falsifying as we reconsidered Webb's previous discoveries. Not only is the James Webb Space Telescope finding galaxies forming 200 to 500 million years after the Big Bang, but also that they are bigger and brighter than astronomers expected. As a quick note, the farthest galaxies seen by the telescope are also some of the earliest galaxies in our universe. The Webb telescope can see them because it is picking up the faint light emitted by them. By the time the light from these far reaches of the universe approaches the telescope, it is in the infrared range of light and no longer viewable to the naked eye. This light has been traveling a long time by the time it reaches the telescope. For reference, it takes around 8 minutes for light to travel from the Sun to your eye. Light from Proxima Centauri, the nearest stellar neighbor of the Sun, takes a little over 4 years to reach us here on Earth. But light is a double-edged sword in the context of these galaxies. It's what lets us study the galaxies, but there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass, because a galaxy's light comes from stars. If you assume a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. But much more of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. As Jorge Moreno, an associate professor of astronomy at Pomona College, said, "It's like if you went to a kindergarten and you saw a teenager." The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe. How old is our universe? The question is simple enough, but as the years go by, it's becoming apparent that settling on an answer isn't quite so easy. Even today, the matter remains open to discussion, as new research could at any moment upend our previous cosmic conception for the age of the billions of galaxies that comprise our universe. In an attempt to explain the shockingly bright, highly structured, and possibly quite massive, galaxies existing so early in the timeline of the universe, a researcher has posited that the universe is roughly twice as old as previously believed. This researcher and others push the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. Well, let's look at these two theories side by side and unpack what's true versus what would need to be true in order to truly determine the age of the universe. First one, it's worth noting that any time you're given a scientific theory, you have to ask yourself, what assumptions are behind it? In the case of the standard model of cosmology, the lambda CDM model, the assumptions are that the laws of physics are given by general relativity for gravity and the standard model of particle physics for the other three fundamental forces. The universe is roughly the same in all directions, isotropic, and the same at all locations, homogeneous if you examine it on the largest cosmic scales. and that, in addition to the known particles that make up our conventional notions of matter and radiation, there also exists some form of dark matter and some form of dark energy, both of which contribute to the universe's expansion, and where dark matter not only aids in, but dominates, the formation of large-scale structure. Within general relativity and particle physics, however, there are some unstated assumptions that are so fundamental to these theories that they're never even talked about. That the underlying laws of physics are the same everywhere and at all times, that the fundamental constants are truly constant, and that the only effect empty space has on light that passes through it is on its light's wavelength, through a combination of the Doppler shift due to relative velocity, gravitational redshift due to the curvature of spacetime, and cosmological redshift due to the expansion of the universe. On the other hand, the new idea put forth by controversial scientist Rajendra Gupta keeps most of the same assumptions in place, but offers a few subtle but important changes. First, instead of assuming that only the Doppler shift, the relative motions of the light-emitting source and the light-absorbing observer, the gravitational shift, the difference in the space-time curvature between the emitting source and the absorbing observer, and the cosmological shift, as the traveling light gets stretched to longer wavelengths by the expanding space-time it's traveling through. Gupta also proposes an idea first put forth by noted astronomer Fritz Zwicky back in 1929, the tired light hypothesis, or the notion that light, as it travels through space, inherently radiates and loses energy as it travels, becomes tired before it arrives at the observer. And second, instead of the standard assumption that the laws of physics and the fundamental constants behind them are constant with time, Gupta invokes an assumption that others have explored previously, that the fundamental constants c, the speed of light, h, Planck's constant, and g, the gravitational constant, aren't actually constant in time, but vary. In particular, they vary in a special way, changing altogether, so that the combinations of these constants that govern atomic transitions and emission-absorption lines that we wind up observing won't change as we look to either more distant galaxies within the expanding universe. One of the remarkable features of science is that if you have multiple different models that have different underlying assumptions that go into them, there's a scientific way to tell which one is superior. It isn't to look at personal preference, elegance, aesthetics, or simplicity. Instead, there are two key questions that we have to evaluate. 1, which theory has fewer free parameters? And 2, which theory better fits the full suite of data concerning the universe? The reason we look at the number of free parameters is simple. A theory that can make the same predictions as another but with fewer assumptions or required inputs is a superior physical theory to one that requires more assumptions, required inputs, or free parameters. But in order to be considered a success, you have to consider everything that we observe on all scales, from subatomic ones to cosmic ones, is consistent with and not in conflict with your theory for how the universe works. In his paper, to his credit, Gupta looks at a few important pieces of the puzzle. He looks at the inferred distance to supernovae seen at a wide variety of cosmic distances, and shows that not only are they consistent with the standard cosmological model, the lambda-CDM model, but also with a version of the lambda-CDM that includes tired light, what he calls lambda-CDM plus TL, with a model with covariant coupling constants, what Gupta calls CCC, and with a model with covariant coupling constants and tired light included, or CCC plus TL. Well, yes, he's including 2 extra free parameters in his theory, as opposed to the standard lambda-CDM, in the form of a tired light component to the universe and also in the form of a set of covariant coupling constants. This remains consistent with what we've observed for how distances, redshifts, and brightnesses appear in the expanding universe. In addition, Gupta also notes that, by introducing tired light on its own in addition to the standard ingredients in a lambda-CDM cosmology, He arrives at a universe that ages much more slowly at very high redshifts, corresponding to great distances. Whereas a standard lambda CDM universe has experienced only 13.8 billion years since the hot Big Bang, a lambda CDM universe with tired light would be about 6 billion years older, up to about 19 and change billion years old. Additionally, much of that aging would come early on. Whereas galaxies seen at the limit of Hubble and near the edge of JWST's capabilities, at a redshift of z equals 10, would only be about greater than 400 million years old in the lambda CDM model, they would be about 2 billion years old in the lambda CDM with tired light model. Furthermore, by introducing both covariant coupling constants and tired light, he can increase the total age of the universe to a whopping 26.7 billion years old. At a redshift of z equals 10, instead of greater than 400 million or even greater than 200 billion years, the universe would already be about more than 600 billion years old, an impressively very large figure. Gupta contends that whereas JWST has shown us galaxies that appear brighter, more massive, and more evolved than they had been expected to be seen so early on, is modified cosmology, with tired light and varying coupling constants, these galaxies suddenly fall into line with expectations. But as we said earlier, science isn't about solely looking at the data points that favor your explanation. That's what we call cherry picking, and that's a surefire way to lead us towards biased conclusions. There are key pieces of evidence that would show up if either light got tired as it traveled through the universe, and or if the fundamental constants have changed as the universe has evolved. They would show up in extremely telling ways, and we can actually list a few of them off before looking at the evidence that the universe itself presents on these fronts. Here are 4 of the most major ones. Number 1. Tired light would add a blurring effect to distant galaxies. When Zwicky first proposed the tired light idea in 1929, it was one of the few astronomical ideas that wasn't viable even at the moment it was proposed. The reason? Zwicky himself recognized, even prior to publishing the idea, that if there was something causing the light to get tired, i.e. something for it to interact with and that caused it to lose energy, then more distant objects wouldn't just appear redder, as their light's lost energy would deboost it to longer wavelengths, but would also appear blurrier. In fact, those more distant objects would be blurred by a greater amount than observations would have permitted. Look at this image here. You can see 2 objects. One that's a massive foreground object at a relatively shallow redshift, and one that's a much more distant background object at a much higher redshift. If the tired light scenario played any role in causing the redshift of these objects, the more distant objects would be more severely blurred. Yet, in this, as well as other images that show nearby and high redshift objects together, no such blurring has ever been observed. The universe doesn't get blurrier the farther back we look. The optical limits of our telescopes and observatories shows that, 100% of the observed redshift is cosmic. Number 2. Tired light would eliminate cosmological time dilation. Here's a fact that we don't often think about. The more redshifted an object's light is, the more time it takes for the same number of emitted wavelengths to be seen by the distant observer. An object at a redshift of z equals 1 would have its wavelength stretched by 100% over an object that was in the here and now at a redshift of z equals 0. In order for the same number of crests and troughs of the wave to pass us by, because they only arrive half as frequently, we'd have to wait twice as long. This results in a very interesting implication, that when we look out at the distant high redshift universe, we should see those distant objects exhibit a cosmological time dilation, where their clocks appear to run slow from our perspective. We've seen this for a variety of cosmic objects, including for distant supernovae, where the more redshifted a supernova is, the more its light curve gets stretched out in time. This was recently confirmed at greater redshifts by looking at a class of objects quasars that appear to tick with a regular periodicity. Going all the way back to when the universe was under 1 billion years old, 100% of the redshift, again, appears to be cosmological, and these quasars show a time dilation of exactly the amount predicted by our standard lambda CDM cosmology. With no difference observed, none of the redshift can be chalked up to tired light. Number 3. Tired light would change the thermal blackbody spectrum of the cosmic microwave background. This is a very, very big one. Whereas the galaxies we're looking at go up to a modest redshift of z equals 13, which is where the current cosmic record holder presently sits, the cosmic microwave background was emitted back at a whopping redshift of z equals 1089, when the universe was only 380,000 years old, according to the standard lambda CDM model. When light redshifts due to cosmological expansion, it maintains its black body character. The spectrum of how photons are distributed remains in thermal equilibrium. The number of density of photons, however, has to drop to match that of a cooler black body, and in the lambda CDM, it does. But if light were to get tired instead, the energy of the individual photons that compose the cosmic microwave background would still drop, but the number density wouldn't change. As a result, the spectrum of tired light that appears as a cosmic background would not obey a black body spectrum. And yet, the cosmic microwave background is the most preferred black body ever measured. The only way to save this aspect of tired light cosmology would be to observe some sort of non-black body component to the cosmic microwave background, but to date, none has ever been observed. And finally, number 4. Evolving coupling constants wouldn't just affect the distant universe, but would appear in laboratory experiments here on Earth. But there's an independent set of constraints we can put on Gupta's second idea, the notion that the coupling constants change over time. Atomic transitions are governed by changes in two of the fundamental constants, c, the speed of light, and h, Planck's constant, while cosmological changes are sensitive to g, the gravitational constant, as well as c and h. But on Earth, we have independent ways to check these constants independently, including how they've evolved over time. While laboratory measurements of the electron magnetic moment, the spin-flip transition of hydrogen, and the equivalence of inertial to gravitational mass all provide good constraints, we have a far stronger one that proves the constancy of these fundamental constants over time, Earth's only natural nuclear reactor. By looking at how the nuclear reactions occurred under the natural conditions that existed on Earth 1.7 billion years ago, we can determine that the fine structure constant, which depends on the electron charge, the speed of light, and Planck's constant, changes by less than 0.3 parts in 10 quadrillion, that's 10 to the power of 16 per year. That constraint is, quite literally, billions of times stronger than what Gupta's varying fundamental constant explanation would require. It is for these reasons, among others, that we can overwhelmingly conclude that even though Gupta's toy model of the universe may be fun to play with, it has no basis in reality as far as either tired light or covarying fundamental constants are concerned. Observations of the universe, from in-focus distant galaxies to cosmologically time-dilated events, to a black-body cosmic microwave background spectrum, to nuclear reactors right here on Earth, all show that these ideas do not correspond to our actual reality. It might be fun to explore or theorize about, but at the end of the day, the universe is our laboratory, and whatever it reveals to us about how nature actually behaves is what we have to go with. The universe might not be fully understood, but its age is definitely 13.8 billion years old, and absolutely cannot be 26.7 billion years old based on the evidence at hand. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.